Classification machine learning is the core foundation of any data science and AI projects. In this video, we have picked a very popular dataset from UC Irvine Machine Learning Repository and build end-to-end machine learning model all together, from importing the data, importing necessary modules and libraries, exploring and visualizing the data, then pre-processing, training the machine learning algorithms, not only one, but multiple one of those, and tested the model's performance in general. Pick the best model. Then we have saved the model locally and deployed into a web interface. Without any further delay, let's straight dive into this. Let's make the complex problem super easy.
As I mentioned earlier, we will begin with environment setup. We will need to have a dedicated virtual environment for this specific project. To do that, I will install and activate the virtual environment dedicated for this breast cancer prediction machine learning model. Then we will install all the necessary libraries and modules, including NumPy, Pandas, Matplotlib, Seaborn, Streamlit, etc. And then we will import necessary libraries and modules that is required for the model. And then we will load the data set, and we will perform the basic data exploration, including understanding how many rows and columns we have in our data, what does the statistical distribution look like, if there are any missing values in the data, etc. And now we will perform some basic data visualization to have a good understanding of the data. Then we will perform the data pre-processing that prepares the data for machine learning model. That includes scaling the data, normalizing as necessary, etc. Then we will initialize and train the machine learning model. Then we will perform the prediction on train and the test set. Then we will evaluate the machine learning model's performance. How are the models performing on the unseen labels? Then we will save the models locally, preparing for deployment. And then I will quickly walk you through on a Streamlit web application that can be used to deploy the model into production if you aim to, and we will run the app locally since the production deployment can be in the company's production environment. Here I will show you how app works in local web browser. So let's straight dive into this. Let's begin with installing and activating the virtual environment. I will go ahead and open the terminal, that is the terminal and the new terminal in the VS Code at the very top menu. And I will make sure that I'm in the home directory, not in the project folder. So I will do cd space dot dot enter. In the Windows computer, it will be just cd dot dot enter without any space between cd and dot dot. I am into my home directory or the root directory. Now I will create the virtual environment here with the same name so that there is no two folders, one for virtual environment, one for the project file. I want to keep it standard. So to do that, I will say Python 3, or you can do Python as well, -m. You will call virtual env. That stands for virtual environment. And I will give the exact same name as my project folder, breast-cancer-predictor. That will help you to organize the virtual environment and the files easily. So I will say breast cancer predictor, hit tab, and that will fulfill the complete name of the folder for me. I'll hit enter. Now my virtual environment is created. All the files of the virtual environments are ready. Now I will continue on this virtual environment. So after I have installed the virtual environment in my folder, I will go ahead and change the directory to be my project folder. I will say cd and then breast cancer predictor. Look at this here. I do not have a different folder for the virtual environment. All the virtual environment components are within my project folder. That is why it's easy to manage and easy to access the files and folder as necessary, and also easy to activate and deactivate the virtual environment. So let's activate the virtual environment since I'm already in my project folder. So I will simply say source bin/activate. If you're using Windows computer, you can simply say scripts/activate. It will activate the virtual environment. I will hit enter, And now my virtual environment is activated. Since you can see within open and close parentheses, you can see breast cancer predictor. That is my project folder and also the virtual environment. So my virtual environment is activated. Now here I will install all necessary modules and libraries required for this project. So if you want to just install them as I'm installing, please feel free to pause the video and go ahead and install all the necessary libraries and modules. I will say pip install, then I will say numpy with just space, pandas, matplotlib for the data visualization, seaborn for advanced graphicals data visualization, scikit-learn for machine learning, and Streamlit for web development, web app development. So I will also install IPY kernel. The reason behind IPY kernel I need to install here is I'm running VS Code, and running Jupyter Notebook in VS Code, I need to install the IPY kernel module. So I will hit enter, and all the necessary libraries and modules are being installed, and they will be completed very shortly. Now, as you can see here, I'm ready with all the necessary libraries and modules already installed, and now I can go ahead and close the terminal and I can continue working in my notebook. So this step is completed. Now the next step is importing necessary modules and libraries that we have just installed. I will begin with importing the basic data exploration and loading the data, then numerical calculation libraries and modules, and then I will next import is the machine learning focused libraries and modules. That includes the libraries that help us to split the data into training and test set, then scaling the data. The values might be, some of the columns may have a very extremely high range of values. Some columns may have extremely low range of values. To avoid any model bias, we need to scale the data onto the same scale, and for this one we are using StandardScaler. Then here, these are the machine learning models that we are going to train, test, and choose the best model for deployment. So here, logistic regression, binary classifier, support vector classifier, decision tree classifier, the tree-based model, and then random forest classifier, the ensemble technique, and nearest neighbor based model. So these are the 5 different models that we are going to train, test, and evaluate, and we will be choosing the best model for the deployment based on precision recall or F1 score. Now here, this is going to be our model evaluation techniques from scikit-learn.matrix. We are going to import accuracy score, precision recall score, F1 score, and classification report. These are the model evaluation technique that we are going to dive into. And then here from scikit-learn, we will be loading the data set load breast cancer. These are the libraries that is needed for this project in general. So as needed more, in case we will be importing more, for example, Streamlit, that may be the one that we need to import into our application.py or app.py file. I'll hit enter, and now all of these libraries are being installed into my Jupyter Notebook. Here you can see that my Python kernel has been selected by default as a breast cancer predictor without me specifically selecting that, because we are on the same directory and the best that identified kernel is the breast cancer predictor, the virtual environment, and the Python that we have recently installed. So as soon as these complete, we'll be diving into the next one, which is loading the data set. So we have imported all necessary modules and libraries. Now let's go ahead and load our data, and that will be with initializing load breast cancer. To do that, before that, I would like to write code for specifically viewing and managing the data. So to do that, what I will do here is I will say pd, the pandas library, dot set option, and here I will say display dot max columns, and then I will choose that to be none. I don't want to set any limit to display the columns. For example, when I'm trying to look at the top 5 rows of the data and bottom 5 sample 5 rows of the data, or the data set that contains many columns, I don't want that to be truncated. So I want to do also same thing for the rows. If I'm trying to display 25 rows or 50 rows, I want to see them all without any dot or any truncation. That is why I'm going to use these max column and max rows function from pandas, and that will give me the full visibility of rows and column that I want to see in my data set. So it's just more of the visual aesthetics. Now time to load the data. First of all, I would like to initialize the data set. That will begin with saying data equals load breast cancer, which I have already imported right here. So this function will give me the initialize the data set. And then I want to load that initialized data by saying pd.dataframe, pandas data frame, and I want to load from the data object, I want to load the data. And then the columns that I want to define is from data object, I want to get the feature names. That's going to be our data set. So if I hit run, my data set is loaded. So I want to confirm if the data is loaded or not. And that's going to be as part of the basic data exploration. Let's start exploring and understanding the data. That begins with everyone's favorite, that is df, the data frame, dot head. That gives us by default first 5 rows from the data. You can always put 5 here, that's okay. But if you don't want to put 5, that's totally fine. It will display the first 5 rows of the data. As we can see here, our data set contains this is index column, and now the mean radius, mean texture, mean parameter, mean area, mean smoothness, and bunch of columns that we have. And it looks like we have all numerical float type of data. So here all of these are our data columns and the first 5 rows of our data. You can choose to see more or less than 5 rows. For example, if you want to define any specific number of rows, you can define like 3, and that will display the 3 rows. Or you want to see more, then you can define 10 there. So the Python indexing begins with 0, so you will see 0, 1 through 9. And that's how you can look at the first 5 or 10 or 3, whatever number of rows you want to visualize or you want to look at. Another way you can look at the data is df.tail. That will give you the last 5 rows of the data. So if you hit enter, you will see our data has last row as 569 rows, because we know that Python indexing begins with 0. That means we will be able to see 568 here. That means there are 569 rows, and we will look at how to even check the rows and columns in a moment. So you can define any other number of rows here that will extract last that many rows from your data. So for example, I will just add a comment here, last 2 rows of the data set, in this case of the data set that we have. So that's how you can look at the last 2 rows, or if not defined, last 5 rows. You can also have a look at sample X number of rows. So basically, if you don't define anything here, it's not like tail or head that will give you the random, or that will give you the default 5. You have to define how many you want, how many rows, sample rows you want to look at. What exactly this does, it will pull the randomly shuffle indexes for you, and it will pull the rows for you, that many rows for you. You can say 7 or any number, and all the index value will be changed. It will shuffle the data again, and it will give you the shuffled rows for you, 1 2 3 4 5 6 7. And you will see all the columns here that is available within the data. That's how you can pull a few to many rows to look at the data, understand how does exactly the data look like. That will give you idea of, hey, there are some columns with very high value, whereas there are some columns with very low value, which introduces the need of scaling while training the machine learning model. So that's how it gives you the good understanding of the data. Now the next thing in the data exploration is df.shape. that will give you the number of rows in the data and number of columns in the data. You can nicely format that by saying shape 0 and df shape 1, and format the print statement with f string by simply adding the curly braces with opening and closing at each of those values that you want it to be printed. And if you want to add some text within those, you can definitely do that, and you want to make sure that your opening closing parentheses are fine and your quotes are there. So you can say there are these many number of rows and these many number of columns in the data. This is how you can format and organize your response, your print message, so that if you're handing over this notebook to somebody, this is super clear, the outputs are much more readable. Then additional few things that we want to explore here is df.describe, and that will give you the statistical description of your numerical columns. In our data set, our most of the data is of numerical format. So if you scroll from left to right, you will see many of the statistical values of the data. For example, for the mean radius, the count of number of records are 569, as we know from our number of records. Average mean radius is 14.13, and the standard deviation of mean radius is 3.52. Minimum is 6.981. First quartile is 11.7, and the median is 13.37, and the 75th percentile is 15.78, and the maximum is 28.11. We can see that the difference between the 75th percentile and the maximum has a significantly large difference, and that is why we can see that mean is slightly larger than the median value, as we can see that the data is right skewed. Same way, you can look at any other column and understand how does the statistical distribution look like in the data, and you can have a good understanding about the data, so that if necessary, you can perform the outlier detection, anomaly detection, and even if necessary, removing outlier or treating accordingly are some of the ways that the data, this statistical description gives you. That includes the standard deviation, how is the spread of the data from the mean. That's what the standard deviation explains, and you can also understand how far away the values are from the mean. For example, here, or from the 75th percentile in this case. Look at this here. The 75th percentile is 782, and the maximum is 2500. That's almost 4 times larger on just one quartile. And that way you can also see is 50th percentile, or the median value is 558. However, the mean value is 654. That means the data looks extremely right skewed, and that means it has a larger value or rare larger value towards the right side of the distribution. And this is how you can understand and look at the standard deviation, significantly larger. That means this data, this column specifically, has extremely right skewness, or has extremely outlier values towards the right. Same way you can explore the data and understand the basics of the data set. Now you can also add .t here. That will transpose rows to column and columns to rows. That will put all of those columns that were in the columns now are in the rows, so that you can easily understand statistical distribution within your visual area. This is how you can explore the data. And last thing we are going to look at here is the missing value, if our data has any missing. So you can do that in two different ways. One is df.info. That will give you overall information about your data. That includes what type of data it is. It's a pandas data frame that has 569 rows and 30 columns. So here in this specific section of this output, you can see that the column names and shows how many non-null, means no missing values exist in the data, and what are the data type for each individual columns. Looks like all of those we have the float 64 or data numerical values with decimals. So this is how you can explore and understand the data. And here all those 30 columns that we have in our data is a float type or data numerical value with the decimal. We also say them double in the data type. So that consumes about 133.5 kilobyte of your compute resource in the computer. So this is how you can do one way. And another way of identifying if we have any missing value is simply df.is null or is na, and you can do dot sum. That will give you the column names and if we have any missing rows into our data. So you can look at all of those all together, and we can see that there are not any missing rows into any of the columns into our data. So this is how you can explore and understand the basics of the data. That will give you a strong foundational understanding of how does your data look like in general, if you have to perform any data cleaning, and necessarily if there is any issues with the data. Now, immediate next thing we want to do before data visualization is setting up the target variable. If you see here all of our columns, and one way to look at the columns is df.columns. If you look at here, there are many things, dimensions, or the features that we have here that shows how does the specific information of the feature look like, but does not necessarily represent any target feature in this specific data frame. And now that target feature is hidden within the object right now, that object we had as a data. So to extract the target feature, what we are going to do is we are going to define a new variable called target here in our data frame, and from the data object we are going to extract the target, and that will give us the target column. And if you look at our data now with the column names, you will be able to see the target being added here, which was not earlier. That was the last column. Now target is added into our data frame. And now if you look at the data again, maybe just a few rows, 3 rows here, and if you scroll all the way to the left, all the way to the right, you will see the target column being added, which was not available earlier. If I scroll up, you will not be able to see that target column because which did not exist earlier. It was the worst fractal dimension was the last column in the data. Now we have the target column added, and that is available within our data, and that we need the target feature or target column in order to be able to build and predict using the machine learning model. That was a quick data exploration. And now let's visualize with some visuals, and we will straight dive into the pre-processing step. Data visualization is really crucial part of any machine learning, any data science project. That gives you a good understanding of the data. That will help you to understand how does your data look like, if there are any issues in the data, how does the distribution of any specific column or columns look like, how many columns have any associations with the target variable, what is the magnitude of the association or the correlation of one column to the another column, etc. There are many questions can be answered using data visualization. Here in this video, I will cover just a few data visualization, and there is another, the extensive video specifically dedicated to the data visualization into my YouTube channel. Please do not forget to check that. That will give you a hands-on practice on what all are different ways that you can visualize the data and build a strong understanding about any data set that you are going to use and build the machine learning model or models. In this visualization, we are going to create the count plot, and we will be using Seaborn library for that. Seaborn library has the higher graphical visualization that has many additional visualization than the matplotlib. And if you have not already subscribed to my YouTube channel, please do so. that will help me to and be encouraged and make more videos like this and help you to learn and to grow in the data science. We are building a data visualization that contains the target feature being X. In the X axis, we're adding target feature and from the data. So here we are counting the target feature values. If you quickly look at how does our target feature look like. So here, if you say target and do dot value counts, this way you will be able to see the count of labels. So 0, target 0 means the patient has no cancer, and target 1 means patient has a cancer. So in this case specifically, we are calling malignant to be 0. That means the patient does not have a cancer, and then here 1 means the benign, that means the patient has cancer. So it looks like 357 records or 357 patient had cancer, and then 212 patient did not have a cancer out of our given data set. So that we will visualize into the count plot, and I will put the color legend to be the target as well, and I will set up the title. So title of the visualization would be distribution of malignant and the benign patients. And X label, so we'll add some label to the X axis, and we will put the Y label to the count to be the count of the records. And finally, we'll say plt.show that will show the visualization. As I hit enter, you can see that I have a nice, beautiful graph that shows visually how does my target variable values look like. So you can see here, it looks like just above 350, we have the patient with cancer, and then just above 200 patient, we have with no cancer. So that's how our data looks like, as we have seen over here, and that thing we are visualizing in the graph. Visually understanding the data is much more effective than just rows and columns. That is really powerful way of understanding the data. Now, one more visualization I want to visualize is the scatter plot. Scatter plot gives you a huge visualization and data understanding that builds how does each individual values in column A stand with the column B. What is the association or relationship of two features? So here we are going to have a figure size here 8 by 6, and we will call seaborn scatterplot function that will take column value in x-axis and another column in the y-axis, and what is the color legend that we want is to be target, and from our data frame alpha the colored aspect to be 0.7. So, and we want to set up a title, so you can add X label, Y label, etc. So here we're just adding the radius versus texture and clear separation. That will give us the good understanding of how does the relationship of mean texture look like with the mean radius. So having a patient with high mean radius, does that mean also the patient has high texture? In this case, that doesn't stand really true. So in this specific data set over here, so mean radius being barely 13 or 14, the customer has over 30 of the mean texture. So some of the values represent that trend. It looks like it has somehow positive correlation, but the values are almost everywhere. However, one thing is clear over here. So all of those patients that have the cancer looks like to be most of the patients are around very less mean radius and very less mean texture, except a few outlier conditions here. Now the customers or the patients with very high mean radius and high mean texture, or maybe not really high mean texture, so high mean radius and almost same as mean texture look to be having no cancer. That means it looks like if the mean radius is larger and the mean texture is lower value or moderately low, then that patient looks to have no cancer, but if the mean radius is really small, mean texture is also small, small to large, then the most of those patients looks like they have a cancer. You can change any other column here and then visualize it. As far as their numerical column, the scatter plot will be able to give you a good hands-on understanding about the data set. Last visualization we are going to build here is the correlation heat map. So that way we will be able to understand how does the correlation look like between two or more columns. For example, here in this correlation heat map, first of all, we are also using seaborne heat map because of graphical interface, that really beautiful, nice interface that it has, and better color range we can choose from. That's a really nice updates that we have on the visualization comparing to Matplotlib. So here we're looking at the very first 10 columns within our data, all the rows and 10 columns. We're building a correlation heat map, and that is due to the large number of columns, large number of features we have within our data set. We just pick that, but you can always choose to select all of those. That's totally fine too. Annotation equals true. That means we want the values to be displayed within the correlation heat map, and we want to add the color map to be cool to warm. We are doing the 2 decimal value to be displayed, and we can do 3, you can do 4, but it will have really hard time to fit within the visualization. Now we will have a title, that is right here, the title, and we'll visualize the graph with the plt.show. So right here you can see that there are some columns. You can look at over here, 0.82 mean radius to concave points that have really high correlation, almost very positive correlation, close to 1. And that means as the concave point values increase, the mean radius also increases. We can prove that within the scatter plot. If we look at the concave points and mean radius, let's look at that here. So mean radius to concave points. Look at this here. As the value of mean radius increases, the value of mean concave points also increase. However, when you see the mean concave point at some level, so after some level, all of the patients that have extremely high mean concave points and mean radius, they are non-cancerous patients. However, if you look at the yellow or orange color, they are the patients with the cancer. They have really low mean radius and low mean concave points. This is how visualizing with the scatter plot will really help you to understand the data and the distribution and the relationship of one column to another column. Likewise, the darker red color means close to perfect positive correlation. Darker blue color means columns have negative correlation, and the almost white color means there are correlation exists, but it's not magnificently large values of the correlation. So this is how you can visualize and visually understand the data and build your strong foundation behind your data before you enter into data pre-processing for the machine learning model and training the machine learning model. In this section, we will pre-process the data for machine learning models. That means we are preparing the data so that the machine learning model has no problem on accepting and being trained with that data and predict accurately. That includes splitting the data set, whole entire data, into the training features and the target variable, and splitting the data into the training set and the test set, and then scaling the data, etc. So let's begin with splitting the data into the training features and the target variable. So here, what I would like to say is capital X, upper X, that will be df dot drop. If I drop the target variable, it becomes all the remaining columns are the training features. If you say df dot drop from data frame, we are dropping the target feature at the column level. That will give us the all training features, or X. Now, why? You already guess. df target is that simple, and that will be our target variable that we are going to train the machine learning model and predict target on the data set that doesn't have a target. So let's run that, and now we have x and y. So if you just say x dot head, you have all the columns. There is no more target column included here. And then if you do y dot head, that will give you just straightforward the one column that is our target column. So this is how we have splitted the data into the training features and the target variable. Now the next thing is going to be performing the train test split. So what exactly train test split is doing here is we are going to split the data into the training set and the test set. That means using the training set, we will train the machine learning model and help the model to understand and learn the pattern. Using the test set, we will actually test the capability of the machine learning model. In that case, on that test set, we will not provide the label to the model. We will actually ask the model to predict the label. Now, once the model predicts the label, we will compare that our original label that we had but never provided to the model, and we'll compare that with the model's predicted label. And if they match, that's the accurate prediction. If that does not match, then that is inaccurate prediction. Let's perform the train test split. So x train, x test, y train, and y test. And we'll call the function that we have imported is train test split. And that will take the variables, first of all x, of course the training features, y, the label, and then I will set up the test size to be just 15%. Since our size of the data is significantly small, I will just keep 15% to test the model's capability. I will provide 85% of the total data to be in the training set so that model has the maximum data to learn from, and there are just a few records to test. Anyways, we are just testing either model is doing great or not. 15% of the total records are just fine for us. And I will set up the random state to be 42 to maintain the reproducibility of the values if we run the code multiple times. Okay, so that has given us the training set, test set. You can validate by simply checking the xtrain dot shape of the xtrain dot shape, and then you can see here 483 records and the 30 columns. And you can also on the same one xtest dot shape, and that has given us 86 record and 30 column. That has all the columns that is available in the test set as well, just confirming how many rows are in the test set and how many columns are in the test set. And you know that y train, y test, just one column and rest of the rows in the data. So if you want to confirm that, you can always check the y train dot shape and then y test dot shape. And now these are ready to be used on as a training set and as the test set within our machine learning model. The next thing we have noticed into our data is our data values within each columns are not very same on the scaling. So if I would simply show you the first 5 rows of the X train, look at this column here, mean radius, that is around 12, and then 12 again, 17, etc. However, if you look at the mean parameter, that has 83.97, 119, 78, etc. How about mean area? Even larger numbers. And those scale don't match. Mean radius here and the mean area do not match. Mean area versus the mean smoothness do not match. They are very different on the scaling or the range of the values. And that being said, the machine learning model in this case would be super biased on the prediction towards mean area, and that will not give the justified prediction using the mean smoothness or compactness, concavity, and then concave points, and then mean symmetry, etc. So to avoid that situation, we will need to perform the scaling of the data. So what we will do here is we will initialize the scalar called StandardScaler, or that is also called z-score scalar. will initialize the scaling technique, and that will scale the range of the values if they are normally distributed from -3 to +3. But again, if those are within the 3 standard deviation, there might be possibility that there are more than higher than -3 and +3 as well. So here we have xtrain, we'll call scalar dot fit transform, and I will pass on the xtrain data or training data. And then I will pass on the test data as well. I will say scalar dot transform x test, right? And then I will hit run. Once you have scaled the data, they have been transformed and scaled into, this has been transformed into array. So if you want to quickly look at the data, then xtrain, and if you hit enter, you will see that the values are very much scaled within very small number, because the values were not the same as same in the range while looking at multiple columns. And if you look at the x test in the same way, you will see the similar the transformation of the data. That's how we scale the data and bring into the same scale to effectively and accurately train the machine learning model, so that the model does not interpret the data incorrectly. Now, once we have scaled the data, it is time to perform the most important part in the project, that is initializing the machine learning model, training them, and perform the prediction, and then evaluate the models. So to do that, here, as we mentioned, we are going to train more than one model, here specifically 5 models. So I will initialize the variable models, and within that, I will provide the initialize 5 different models as we discussed earlier. So those models are logistic regression, support vector machine with linear kernel, and support vector machine with RBF kernel, and decision tree, random forest, and k-nearest neighbor. I have created separate videos explaining about each individual machine learning algorithms in detail. Please do not forget to check those videos. That will keep your concept super clear if you do not know about these models in depth. So I will initialize these models. Now our models have been initialized. So model name, here logistic regression, initialized as a logistic regression, and then support vector machine with linear kernel, initialized with as SVC, kernel equals linear, support vector machine with RBF kernel, so SVC with the kernel being RBF, decision tree, so here decision tree classifier, and then here random forest classifier, and k-nearest neighbor classifier. So that being said, this is a binary classification problem. We are predicting the target being 0 and 1. That is binary classification problem. That is why we are importing all classification machine learning algorithms. Next step is to be able to train the model once initialize them. So what I will say here is I will initialize the variable to store the results of each of these models. So I will say store the results. I will initialize something variable or list called results, and in that what I will do is I will write a for loop that will go through the name of the model right here, the name of the model, logistic regression, and it will take the model, actual model, and in models dot items, it will go through the name of the model and the actual model. These are the actual model, the values from models dot items. That's how we are iterating over each individual components of the model dot item with the name and the model. We'll say model dot fit using the xtrain. So we will fit the data xtrain and ytrain. So we'll provide the training set of the data, and then model will be fit and train on the training data set. So we'll go through each individual models, and then we will train the models on the training set. Then the next thing is going to be perform the prediction on the training data, and then we will also see how does the performance looks like on the testing data as well, so that we can understand if the model has bias problem or overfit problem. So here I will call the variable called train pred, the training prediction, and I will call the model dot predict on what? Training data. I will ask the model to perform the prediction on the training data. Now the next is test pred. That being said, I will ask the model to predict on the test data, so that I can, first of all, these are this X train, the model already has seen the label. And I will ask the model to perform the prediction on the same data that it has been trained with. Also, I will ask the model to predict on the test X test, which doesn't, this one, we are providing the X test, which doesn't have a label right now, right? But we do actually have a label for us, which we have not exposed to the model. So we will ask the model to predict the label, and later on we will compare the predicted label with the actual label that we do have, but model has not seen before. Now, once we do perform the prediction, the next step is to store the results into the results empty list that we have initialized over here. So what I would like to do in this case is say results.append. I would like to append all the results of the prediction of the models, different models. I will say the column in that results, I will say models, and then I will give the name of individual models. Here we have the name and the model, which model, and then which model it is that we have used and we are storing the result of. And I will say training accuracy. That is, I want to check how well the model did on the training data. So I will call accuracy score function, and I will pass on yTrain, and I will say train prediction. So what this will do here is it will look at the actual label and predicted label. Why train pred, actual label, and the predicted label. Model has already seen these labels. Now we have still asked the model to do the prediction so that we can calculate the training accuracy. So this way we can evaluate how well model did against the training labels. Now the next thing is the test accuracy. So here, same way, we'll call the accuracy score function, and here instead of yTrain we are giving yTest. And now the next thing is, as you might have already guessed, that is test pred. That way we can compare the actual test labels on that 15% of the data against the predicted labels by the model on that 15% data, which model has never seen the labels. That's how we will be actually able to see how well the model is doing, how much model has understood from the training portion of the steps that we have already provided to the model and have given chance to learn from the data. Now the next thing is going to be storing the precision score. So I want to store the precision score, and I will simply say precision score, and then I will, same way, I will do that on the test set, yTest, and I will say test pred. So I'm calculating the precision score against the test set. And same way, the recall score as well. And I will call the function that I have imported already, the recall score, and I will give the test set and then test prediction. So these are some of the model evaluation techniques. And the last thing we will do is F1 score. So harmonic mean between the precision and recall score. So I will give the same yTest and test prediction. So these are the model evaluation. Here on the precision score, what exactly we are trying to see is out of all predicted one, how many were actually one. That's a precision score. Recall score is out of all ones, how many model captured as one. So that's the idea here, and this is the harmonic mean between precision and recall. That's the idea. These help us to understand the actual how well the model is doing, and accuracy is definitely another one strong and another way of evaluating the model's performance. But remember, accuracy is not only the best way to evaluate the model's performance. So that's how we are evaluating the model's performance and storing all the results with the name of the model, so that we can see which model did how much good or which model did how much bad on the model's performance in general. So I will run that for loop. And now, since our data set was significantly small, our model training and the prediction and evaluation ran significantly faster within 0.1 second. But if you have a larger set of the data, that may not be always the case. It might take so much of the time to train the model. So much of the time means sometimes hours or even days or even weeks. If you got powerful models and you have a significantly large amount of data, means hundreds of millions of records you have to train with, then it may go up to several days to complete the training of the models. We have actually trained, predicted, stored the performance results into results list. Now it is time to go ahead and check how did all of these models that we have trained with, all of these models we have trained, have done on the data. That's what we need to test here. First of all, we will convert the list results into data frame for easy view. So into data frame, it's going to be really efficient to look at the values much more easily. So if you just look at the results right now, it might look pretty bad. So it's really difficult to interpret. So that is, of course, into the dictionary format. So now we are going to convert that into the pandas data frame. To do that, I will say results df, the results data frame, equals pd.dataframe, and I will call results on that, and I will say short values. So I want to see which model did the best job, which model did not, fail to do the good job, and so on. So I will say by equals, and I will say test accuracy, because I want to check by the test accuracy, how well the model did in the test data. And I will say ascending equals false. I want to have the descending order so that I can see the higher value first and the lower value after that. And now, once I do that, I can now see the results data frame or results DF with nice organized table. And you can add some rounding, because after decimal we have a significantly large number of values. So you can always perform the rounding on that. To do that, you can simply say results df equals round, and you can pass on the results df again. If you do that, now our values are significantly rounded, so you can define how many decimals you want to see. Maybe 3 decimals are very nice representation. That way you can actually see the real performance of the model. Look at this here. Logistic regression model performs significantly the best as part of the test accuracy, because our values are sorted by the test accuracy. So test accuracy 0.977 and training accuracy 0.988. That means the model does not have so much of the overfit problem. Of course, the test accuracy is slightly lower than the training accuracy, but here precision 0.964. That means out of all predicted positive as 1, predicted 1, 96% were actually 1. Recall, it captured all the patients. So that means a recall here, out of all cancer patients, 100% of those were captured. And then F1 score harmonic mean was 0.982. That looks significantly good result on the logistic regression. With the radial basis function or RBF kernel, we have a training accuracy of 0.99, which is great, and 0.977. Both of the models performed really well. So, and then precision score and recall score and F1 score, all of those values are exactly the same. But basically, I would say the SVM model did slightly better on the training side. However, we can also say this is slight more overfit comparing to the logistic regression. But all of these, the great models. SVM with a linear function, exactly nearly the same, but test accuracy is not that great comparing to the logistic regression and SVM with RBF kernel, and all others are also recall score is not that great, and of course also the F1 score is not that great. Random forest, it did a magnificent job on the training data, but it has some overfit problem because test accuracy is just barely 95% and the training accuracy is 100%. That means model has some overfit problem, and we can fix that. If we want to choose the random forest, which is really powerful model, we can do the hyperparameter tuning and we can retrain the model. That may do the great job, but right now it has overfit problem. Precision, recall, F1 score, all of those are slightly lower than the best models. K nearest neighbor and the decision tree perform the worst in that case. High, very, very high overfit problem here, 90% or close to 91 to 100%. That means almost 10% difference on the training accuracy and the test accuracy. Precision, recall, F1 score, all of those values are significantly lower. Remembering the data or memorizing the data is the big problem that we want to avoid. That is why we want to consider logistic regression to be the best model in this case and take for the production deployment. So now, congratulations, you have actually trained the model, trained many models, and you have done the prediction on all of those models, predicting the labels for the training set and the test set for all of these models, and you have stored the results into a nice organized table, and then you have figured out which model is the best performing model within our data set. Now, finally, we can look at visually. We have seen on the table, on the data. Now we can look at the same results visually using Seaborn bar plot. And same way, we are looking at test accuracy and for all the models in the results DF, and we will be using model as a color legend. And then here we're providing the plt.title, that means title of the visualization. And then here we want to set the limit because it might be not so much nicely represented on the length of the bars if the range are significantly different. So we're setting up the range to be from 0.8 to 1. That means we don't have to see the long tail from 0 to 100 because all it matters to us is looking at the difference of the model's performance. So here we are doing plt.show. Now let's run this and see how does our visualization look like. I'll run this and look at this here. So we have got logistic regression as the highest performing model. Here, SVM and logistic regression look very close to each other. But if you look at the table, they are slightly different. Logistic regression, training actually test accuracy, both are the same, right? But here, from the training accuracy perspective, this looks to be a little bit more overfit. That is why we have voted for logistic regression here. And both of the test accuracy, both of the models' test accuracy was exactly the same. That's why the size of the graph or bars are exactly the same. We have found the model, which is the logistic regression, to be the best performing model. Next step is going to be saving the model locally for deployment, the best model, which is logistic regression model that we have already seen. So we will do that using a joblib module. So that's called joblib. That is the file format that we will be exporting the trained model. So to do that, we'll choose the file name, what exactly the name of the file we want to give while saving. Model file name equals, I will say best cancer predictor. So, or I will simply say best cancer prediction model. That's how the model is. And then here, and I will say the extension joblib. And then I will give the scalar file name scalar.joblib. So these are the files required that we want to save into our working directory so that we can use these files on the application development. So now, once we define the variables, next thing is to save the files which is going to be model and scaler. So now we'll say joblib.dump. I want to say, hey, dump the model into my local directory. I will simply say model, then I will say model file name. And also I will say I will say dump, and I will export also the scaler and the scaler file name. So these are the items that we are going to dump into our working directory. So I will hit run, and we have saved our model, that is the best performing model, into our local directory. As you can see here, that scaler.joblib and the best cancer prediction model.joblib have been saved into our local directory, and now it is ready to basically deploy the model into web application. Let's develop a web application using Streamlit. And that I have developed a app.py file. I'm going to take you there, and we'll run the application. And this is the same code, just into one application.py file. And I will walk you through, and I will run the file, and we'll show you how does the model actually look like when it runs into the web application or web page. So let's go to app.py. Here I have designed the app.py that basically the steps are nearly the same. However, only the difference is we already have the file that is best cancer prediction model.joblib. That's a trained model that we are going to straight use into our application. So here we are importing all necessary libraries. That includes the Streamlit, Pandas, joblib, and NumPy. Then here we are in the Streamlit, we are setting up the page title. I want to say Cancer Predictor AI or Cancer Predictor Machine Learning ML model. That's how I want to say, and that layout to be in the center. And here I want to use the cache resource, so it will use the cache memory, and the model doesn't have to load every time when you click on run. So I will say define load assets, and I will call model from the joblib.joblib file. I want to use the best cancer predictor model, and then I want to also load the scaler. That's going to be scaling factor. So we have used the scaler, StandardScaler, that we want to scale the data. So that's why we are loading the scaler together, and we will return the model and the scaler. That is the best cancer predictor model, and the scaler, which is the StandardScaler. And I want to call model and the scaler with the load assets function. I want to call the load assets function. Next is going to be application header. So application I will call breast cancer diagnostic assistant, and I will also have a text that says, hey, enter the laboratory measurements below to get the AI powered prediction or ML machine learning powered prediction. Now, next one is going to be defining on the right side, I want to provide all of those measure values. So what you want to provide in the columns, like radius values, texture, perimeter, and then smoothness, compactness, concavity, etc. So I want to provide the numerical option to provide the numerical input, and the default values here I'm going to provide the placeholder values are these, and minimum value I want the user to provide to be 0. That's a minimum expected value, and the default values are the one that will be displayed all the time even if the user does not provide anything. Now, next thing is going to be generating the prediction within the application. Input data is going to be these data that user will provide. If not, then by default, the value will be selected what has been already by default provided. So I'll provide the input data, and then I'll provide the input array as well to generate the prediction and scale the input. So I'm simply scaling using the scaler that we have also exported from our model training, and we will generate the predictions, and then we'll generate the confidence as well, and then here we will display the results. So we have a divider section that will help us to separate the section for generating the output, and that will be basically the separate divider that will help us to separate the view. If the prediction is 1, then I will say, hey, that's a malignant or cancerous. If the prediction is 0, then I will say, hey, that is benign or healthy. So then it will just create the percentage of the confidence, how much confident the model is, and it will also show the probability score. And that's how it will display the result, and it will just have a disclaimer that, hey, this is not any professional medical advice, this is just educational purpose only, so that the people do not misuse the application to claim something. So this is how we have designed the application, and it is ready to run and give us the web interface, and so that we can interact with the model and generate the prediction. So here, let's open the terminal, make sure that we have our virtual environment activated. In that virtual environment, Streamlit, that's an application we have library that we have actually installed within our virtual environment. We'll say Streamlit, and I will say simply run app.py. If I hit enter, then it will open a browser for me. This is the browser that has been opened as soon as I hit enter into my terminal. Now you can actually provide the values, and you can click generate predictions. As default value over here, whatever is the default value, if I just hit click generate prediction, it says, hey, this is actually malignant or cancerous with 100% confidence. Now if I would change the value mean radius to be just 1, and then perimeter to be, let's say, 10, and let's put something different value, and here, so 1.10, something like that. I'm just making the values here, and then click generate predictions. It says again malignant with 80% confidence. Now values started changing. If I would put 2.10 over here, and then just say 0, so you can say 1.00 and click generate prediction, it looks like benign, the healthy. So, but with a less confidence, only 60% confidence. So this is one of the demonstration of how you can build end-to-end machine learning model from importing necessary libraries and modules, loading the data, and exploring the data, understanding the data, then basic data visualization, data pre-processing, initialize the models, all 5 different models, basically 6 different models in our case. SVM had 2, SVM with a linear kernel, SVM with the RBF kernel, trained the model, and we have performed the prediction on the training set and the test set. Then we have created the model evaluation parameters, and we have stored into a list called results. Then we have later on, we have converted that results list into pandas data frame, and then we have got good idea of which model outperformed and which model did not. Basically, there were all of those models had a good performance, but logistic regression did the outstanding performance, and that's why we have also visualized the results, and then later on we have saved the model locally, including the scaler to scale the values in and make sure that those values are on the same scale. Then what we have done is save the model locally, and then we have built a web application. That web application helped us to look at the model into the web interface, and we were able to get the job done effectively and successfully. And we have built production grade machine learning application, machine learning model. So that's all from me, and thank you for watching this video until the last. And I hope by pausing the video in the middle and by practicing, I hope this added a lot of value on your data science and machine learning journey. And if you really like this video, please do not hesitate to hit that like button. And also, if you have not already subscribed to my YouTube channel, please subscribe, and please stay tuned with my future videos that I'm going to upload, and there are many more videos in the channel. Please do not forget to check those and get the best out of it. And thank you for watching. Until next time, please enjoy learning.